basic concept we've done since 18 to now in the games we've gone over. Everything else is kind of just remixes of all of that stuff, and we'll see if they actually throw something new at us. Alright, I'm going to go ahead and get started. Tonight we're going over 2910 Jack in the Box 2018 robot. The 2018 game was Power Up, so we're back to another pick and place game. This time with these like power cubes. So we'll go ahead and kick off and watch the game animation so we all have an idea of what this robot was built to do.
Pass power cubes for the exchange for power-ups, and ascend to face the boss. Teams may preload up to 1 power cube per robot. Additional power cubes are available in the power cube piles, along the fence nearest the scale, and in each alliance portal. At the start of the match, the plates of the scale and the switches are randomized. During the first 15 seconds, robots are autonomous. They work to cross their auto line and place power cubes on the switch and the scale. Alliances who successfully own their switch and have 3 robots cross the auto line will receive 1 ranking point. During the following 2-minute and 15-second teleoperated period, human operators remotely control their robots. They continue to gather power cubes to place on the scale and the switches to gain ownership for the longest time, earning points for each second of ownership. Human operators behind the Alliance Station wall collect power cubes from the exchange. They can deliver them back to the robots through the return or to their vault. In the vault, power cubes may be traded in for 3 power-ups. Alliances choose when in the match to activate each power-up to gain a temporary advantage during the match. The forced power-up gives an alliance ownership of their switch, the scale, or both. The boost power-up increases scoring for 10 seconds for either their switch, the scale, or both. And near the end of the match, Levitate earns 1 member of the Alliance a free climb. Other Alliance members climb from their platform. If all 3 members successfully climb, the Alliance can face the boss and gain an additional ranking point. The Alliance that earns the most points wins the match and defeats the boss.
Alright. So looking through this game, there definitely were quite a few unique aspects to this game. This was when I feel like FRC was trying to do a lot of new and interesting things. They had a lot of ideas. Some of them worked out okay, some of them didn't. So things that are different in this game, the cubes themselves aren't worth points directly when scored in the scale or the switch. It's only if you have ownership of it. So basically if it's tilted towards your side. This causes a lot of problems because basically once you get control of it, you just have the lead, and so it's easier to maintain control than it is to take it back and start scoring points. And since there's only 3 platforms here, if you control your switch and the scale for more than half of the match, you're guaranteed to win. Or if you control your switch the whole time and then the scale for more than half the match. And so like auto became incredibly important because if you were winning the scale out of autonomous mode, it was very easy for you to maintain it. You had to reach less high, so you could stack cubes easier. A robot didn't have to reach as high to overcome the fact that the goal was lifted away from you. So if you already were winning, it became very easy to continue to win in this game. In addition, it was one of the trickier ones to get ranking points for. You needed your partners to all cross the autonomous line for the auto one, and you needed to put a cube in the switch, but you were also incentivized to put cubes in the scale to actually win the match. So if you didn't have partners who could do autonomous very well, it was hard to get that ranking point. And then the last one, you basically had to get the levitate, which was like power up things. So if you had the 3 cubes in the vault for that, one robot was climbed, and then you had to guarantee you and a partner could climb. And so this led to some teams building what we call buddy climbs, where not only are you climbing your robot, you're also lifting one of your partners somehow. So quite a few teams did that with like forks or ramps or other ways to lift their partner up. We did also see in games like this, we'll see robots that are called ramp bots. Um, in general, no one should ever build a single purpose ramp bot. They're a lot of space. Teams are really bad at driving up ramps. But that basically means is all you had to do was be above 12 inches. It didn't really matter if you were on the touching the bar or not. So they would build like a robot that's like unfolded a giant ramp, and teams would drive up on top of them. The concept seems a lot easier than it is. In general, you should not do it. They've had multiple games where that's a possibility. The only one where it was actually important was 2007, when I was like the only way you could end game, and even then the teams that like lifted the partners were better than teams just out of having them drive up the ramps. Um, yeah, the power up things exist. They ended up not being as consequential as people thought they were. They were a little underpowered. It still just came down to placing game pieces, doing it strategically, and just being fast and quick at the main game mechanics, pretty much like it always does. Um, Relatively simple game basics, like when you get away from all of the fluff, like they spend a lot of time on the power ups and all that stuff. The game still comes down to just picking up game pieces, in this case, the power cubes, which is a little tricky. The cubes aren't actually cubes, they're a rectangular prism, so one of the dimensions was smaller than the other two. Um, so if this cube was lined like it was basically a milk crate in a bit of fabric, and so if it was just on like the base of the milk crate or the top, the cube was a square in that dimension. If it's flipped over on one of the sides, and then that one dimension, the height of the cube normally ends up being smaller, and like the lid isn't there, so it's harder to interact with your like intakes and things. So that was a little bit complicated. Teams decided to do it different ways. There were like movable claws and things that could compress more. Um, or some teams just decided to flip the cubes if they ever got into that one orientation where their intake couldn't work. They would just like flip them or rotate them to get them to the correct orientation to be able to grab them. And then you're basically just placing them in the vault, switch, and scale. That was a little challenging, as you do have to score into the vault differently than you do here, right? Because in the switch and scale, you're basically just placing the cube or you're dropping them. Here, you'd have to push them out through this opening. And so depending on how you intake them and depending on how you push them out, it was a little tricky. It is pretty low. You pretty much have to come out right over your bumper to be able to go in here, or be able to grab it on the floor and kind of slide it in. It is like up a ramp. So this ended up having a little bit more challenges than it initially looked like from just the video, right? It's just like, oh, just putting it in the hole, that should be really easy. That's the low goal. If you didn't do it right, it was not that easy to be super efficient at it. And then the climb, like we talked about, where you can buddy climb, and you could possibly pick up your partner. All right, we're going to look at 2910's 2018 robot. They did a very good job of building a relatively simple robot. There's not a ton going on. It'll pretty much break down to about 4 mechanisms here. And they did take this robot all the way to be Einstein finalist in the Houston World Championship. This was back when there were 2 World Championships for 2017, 18, and 19. We had 2 different World Championship events. One called like South, which was always in Houston, and then one in North, which in 17 was in St. Louis, and then 18 and 19 was in Michigan, was in Detroit. So we do have a little bit of a split, but they were still one of the better robots that year. So we can see them actually play. They're going to start here in the bottom left. We do get different potential places where your goal is. And we kind of see that here where it's red is in the switch position here, and then they're on the scale position on the far side, and then the switch position here. So they could have had all red on this side, or they could have all red on the other side, or the one they did get here, or the mirror of that. Those are the four possible options that they ended up playing with. When the manual initially released, there were a couple others, but those were found very quickly to be unfair, so they didn't keep those in the game. So you do have to get there and keep the switch. They were able to have it out of autonomous, and now they get the advantage of scoring it lower and still being able to continue to place. It was pretty tricky as the more and more cubes got on the scale at the high level of gameplay. This is on Einstein, because it was very easy for the cubes to fall off like you see them do here. And so the opponents are having to stack much higher to try to actually recover and try to start winning the scale. Because if they don't win it shortly, they're not able to catch up in this match. And so the other part of that is also if you're just, once you have the scale or you have your switch, if you can just slow down the game, if you can play defense, stop your opponents from doing things, you continue to score points that entire time. So your goal becomes, once you're in the lead and you have your object scoring for you, you just have to make sure the other team can't take it back. Yeah, you can see red here is never even worrying about the blue scale, or the blue switch, sorry. They're just letting that be completely undefended, but they know that as long as they can keep the center structure, the scale, and their switch scoring points, that's all they have to do. And then we see 2910 come up here. They're going to go ahead and climb here at the end with their partner, so both of them just climb independently. They don't have to do a pickup or anything. 1619 here is... Oh, they also did a tandem lift. It looks like they just both climbed. And then they had another robot get on the platform, but that doesn't matter much for what we're doing. Okay. So that was the basic game. So again, it's kind of that pick and place. Everybody was building really tall elevators to be able to score rather high, and trying to keep their center of gravity low so that they're moving quickly and rapidly back and forth from like wherever they're picking up their cube to the scale. So you do want your center of gravity low so you're not rocking or tipping over too much. And so if we start looking at 2910's robot, we can see that they did a pretty good job of that. There's very little structure or mass up high on this robot. It's basically just the elevator and the little bit of things they use for climbing. And the vast majority of the robot is down low. So the robot shouldn't be tipping over too often, at least. When it does raise up, you are going to have your CG raise when you have your elevator up very high, when you're getting to that 9 or 10 feet high in the air, sometimes even higher for these robots. Okay, so this was 2018, so again, these are less modern components. They don't have the same motors we had, the same COTS components that we have now, that we can just buy off the shelf and add into our robot. So there are some things that they had to manufacture a little bit more. So in their drivetrain here, these are swerve modules. So 2910 was one of the early adopters of swerve, and we're able to do it and compete with it at a high level. These are the modules that would become what we now know as swerve drive specialties. One of the 2910 mentors is the owner of that company and designs the modules. So this is kind of where those got their start in the 2910 robots from this generation. So we can see some of the parts that we still use are pretty similar. So like the fork design here is very similar to what we're still running on our SDS MK4s. They were just using a smaller 1-inch wheel, and like the modules themselves were all custom machined by 2910 back then, before they started making them as a product you could just purchase. But it's that same drivetrain though for the most part. You have this outer rail. This robot is definitely heavily influenced by the fact that it has the full bumper and frame gap to allow a cube to fully slide in, which means they do have to make their frame stronger and complete by basically like making it this giant U. So you have the normal outer rails of your frame, but then you don't have that full front crossbar. So they add a second full lengthwise crossbar and have to put their middle crossbar back here at the back before where the cube's going to fully bring in. And so that still gives you a strong enough um, frame here, but if you do take a hard enough hit here, you could start trying to bend some of these. There's nothing supporting across here at all. So that would be something to watch for as you're doing that, making sure that this is fully gusseted and supported. So you're never taking those strongs of hits. Robots also weren't moving as fast. You didn't have that full field runs that you could really do in this game. There was a lot of there's a lot of structures on the field, so you do have like these full field paths here, but you're normally not going from here all the way to the other side. So robots weren't moving quite as fast at top speed as they were in some of our other games now. Electronics wise, they did it relatively standard. They have some very, very lightened belly pan material where they just had the minimal they needed for that cross support and to be able to mount the little bit of electronics they have down here. So this is just the RoboRio. Then they have another spot to mount the battery with a cage up top to hold it in and like a slot for your battery strap to go around. And they do a similar thing on the other side for their pneumatic compressor mounting and just a small pneumatic air tank here as their accumulator to hold their air for their system. These are the solenoids they use to control the pneumatics. So that's what this is in CAD. If you ever see something that looks kind of like this, these are solenoids on a solenoid manifold. We haven't used pneumatics in a few years, probably won't, but if you're looking through other robots, you'll see this. Same with this. This is the pneumatic control module. So this is what controls this, and they're able to change the position of these cylinders as they need to for their intake. All right. We're not going to go into too much detail about the swerve modules. They're just swerve modules, but out of date compared to what we're able to do now with the modern ones. We can look at the front intakes now, though. So for the cubes, they decided to have a separate ground intake and then basically a holder or scoring mechanism that goes on the elevator. So these two large wheels here and these two small wheels stay stationary. They're mounted directly to the frame. They're pivoting off simple pivot shafts here. And so this will be a stationary shaft, and then you have the bearings riding in the part of the intake that's actually doing its motion. They went ahead and just moved the motor and gearbox. So again, this is like the 775 Pros with the Versaplanetary gearboxes that were really common in this generation of robots from like 2013 all the way into 2022 or so. Versaplanetaries were very, very common. And still are. You'll still see teams use some of them, but just now with the way the brushless motors are, they're just less useful as we have gearboxes for those bigger sim-size brushless motors. The pneumatics here are used to deploy it. So you do have a pneumatic cylinder that when it actually extends is when the wheels are going to be inside the frame perimeter. So at the start of the match, everything has to be inside your frame perimeter, which is basically like the outline of your bumpers. So when this extends, this whole module here is able to pivot around and the wheel will be like locked in into this space here. And then at the beginning of the match, when they're ready to deploy their intake, they can just retract it and bring it out to here. They have this spring here that's able to help dampen it as well. So if for some reason this was to take a hard hit and try to expand even more, it's able to expand into this spring region instead of actually trying to hard hit into the bumper or into the cylinder and be bending the brackets back here or anything. It gives it just a little bit of shock absorption, and so little details like that can allow your mechanisms to last a little bit longer through a long season where they are going to take some weird impacts no matter what, right? So even if this were to run into a wall or another robot was just kind of to push this to the side, it has a little bit of dampening and can give a little bit without starting to like bend or stress any other part of the system. These green wheels are all Andy Mark compliant wheels. So they have molded wheels that you can just purchase, and they can flex and give a little bit. So anytime we're running with a really rigid solid object where like it's not like a compressible foam ball or note or anything. A lot of times you want to use compliant wheels because then you can get um, a lot of that give built into the wheel instead of having to like make the whole mechanism compliant and have it move or anything. The wheel itself can kind of just move and adapt and wrap around the hard corners of the cube. Um, and so there's a couple different sizes of those. And then there's a relatively simple pulley system here. They did do a multi wrap pulley system. So instead of the pulley just directly going to one spot, then like having the belt go to the other, they decided to do a single belt um, that they ran and did the path calculations for. So you basically just figure out the circumference of this path or like the length of this path, and you can figure out and calculate it to where you get the right belt that'll actually fit there as it's going around all three of these pulleys and the idler here in the middle. And so that's able to power both these wheels from that one setup. And then it's just a mirrored version on that other side. And so this was good enough to be able to like have a cube come in at like an angle, and then these can power through and rotate it to where it's going to fit back and have its flat sides here because they want to be able to grab it nice and conveniently on the inside here. I don't think they were able to take them um, in on that short side, but they might have been able to. I don't remember exactly what the gap was, but a lot of teams would knock them over first to get them to the correct side to be able to suck it and hold it tightly when they went up. They may be able to with these red wheels and still be able to grab one of the smaller ones. That's probably what these are for, where you get this gap a lot smaller here. So if the cube is taller on that short side going between here, these red wheels are probably able to hold onto that pretty easily. Okay. Before we talk too much about the elevator, I guess we can go that direction. That's fine. So we can talk about the actual handoff mechanism. Again, this is a relatively straightforward. They have bag motors here. So again, just a small motor to be able to turn these wheels, and then it's just belt and pulley, like we would do most mechanisms for something like this, where you're just going to be spinning relatively fast and then just holding that object into place, holding the game piece in. We have more kind of standard pulleys. They added an extra wheel up here. Things like that is always pretty easy if you just need to extend a shaft to add a wheel. We've done that on our like 2023 off-season robot. We did something similar where we just needed to add a second wheel to hold on to the object a little bit better. These are just one by one, so to be able to have like the bearing set up and the shaft spinning through it nicely, they use 3/8 shafts. So these are 3/8 wide instead of the 1/2 inch that a lot of standard mechanisms are built on. This is a little bit more space efficient. These were Vex blocks that were made back then. These are like molded. You could 3D print your own version of these for something pretty simple like this, and then they just clamped over the tube. They did allow them to set belt distance a little bit. Then you could also, if you needed to, you could drill and rivet the blocks into the actual tube itself. Yeah, so they ended up using the Versaplanetary here a little bit as structure. It reinforces some things. So they're mounting that plate here, and they're basically using the motor and the gearbox as a spacer to be able to mount the other side of their intake. So if they did need to replace this gearbox, they're taking off like a side of the intake, but that shouldn't be too hard to do. It's only a few screws, it looks like. So that's relatively easy. But it's packaged very nicely into there, and it acts as like a whole integrated unit and gives this whole part quite a bit of rigidity there. All right. We can look at the back before we go through the elevator routing. That's one of the main reasons I want to look at this robot is the elevator. But they do have a relatively standard electronic backplane here, so they didn't have a lot of belly pan room since they had to cut out all of that space for the cube. So they decided to do the electronics vertically. This is the PDP 1.0. These are the Talon SRX motor controllers. This is what's powering all of the motors on the robot. And then the radio as well. So I'm going to go ahead and hide that guy. All right. Let's see what's the easiest way to look through at the elevator. Before we do elevator, I forgot about these in drivetrain. So these little wheels right here were just there so they wouldn't get high centered on the ramp. If you go off the platforms here at some sort of strange angle and things, you may run your chassis into the edge of that ramp, like if these wheels are off and those ones are on. And so these just make sure they never get high centered and they can kind of slide off the ramp at any point. Um, and are relatively trivial to do. They just put a couple bearings in the tube and have these, I believe these were aluminum wheels that were just able to rotate on there. Okay, so the gearbox that's running the elevator, before we look at the belt path, again, the motors and energy we had back then were just not as much, and you didn't have encoders built in, so you had to build more complicated gearboxes to be able to do more high quality control of the actual robot. So they have these two sim motors driving their elevator, and since they need two sort of two different things that the elevator is going to do, and they need two different incentives, they have a shifting gearbox. So we talked about that on one of the past robots. And so they're able to change the gear ratio depending on which application they're doing. So if they want the elevator to move up and down really fast because they're just scoring cubes, they're going to shift it into high gear. And then when they want to actually climb, they're going to shift it into low gear so that they get a lot more torque and the elevator runs a little slower, but they're able to pull themselves up and lift the entire 120-pound robot into the air to get those end game points and the ranking point. So these ones are a little bit different. We briefly looked at the other shifter that was called the dog shifter, and it moved like outside of the gears, and they engaged one or the other. There's like a moving shaft inside there. This is what's known as the Vex ball shifter. So this was the COTS version of a ball bearing shifter. I'm not going to go into this too much in here. Let me see the best way to get a view of this. But the basic idea is where this hole is. Maybe we can get a view of this. That's reasonable. Where this hole is, there'd basically be a little ball bearing sitting in here. There's three around the outside here. And they do the same thing over here as well. And so they have these 6 ball bearings in this shaft. And then there's this internal shaft that can slide. And so depending on whether this little raised part is which one it's under, is which one the balls are pushing out. And then that engages the shaft to the cutout that's in the gear. So if we isolate here, you can see the ball bearings kind of ride into these notches on the gear. And that's what actually engages them to the shaft and makes them turn together, allows them to actually transfer torque and power between each other. And so you could change which gear ratio you're running based on what you needed to do. So there's still some applications where this is useful. A lot of times we just have enough motor power now, and especially since we don't want to use pneumatics very often, it's a little bit easier to just add another motor to a system and get double the power output and get your gear ratio into a place where it's where it works well enough for both your high-speed applications and your high torque, heavy lifting applications. Okay, so that's what's driving it. I don't know what this other shifter on the other side is. This is often like a brake. That's my guess for what this is. I'm not sure if it's fully catted. Oh, yes, it is. Okay. So what they did was this shaft here is inside the hex. And so this shaft cannot rotate. And so because of that, if you engage the gearbox to drive this shaft, it can't do it. So this basically acts as a brake since this shaft is in this plate. So if the gear is actually engaged, or if the cylinder is engaged the shaft where it's connected and being powered by the rest of the gearbox, it's not going to be able to rotate. And on the other side, they just left a little sleeve here. Probably didn't even, they may not even put balls in it, because if it's just out over here, it's basically a neutral. this gear can free spin on this shaft all at once. And then when the cylinder retracts and brings those balls in, you lock this gear to this immovable hex shaft, and you get your braking action that way. So there are ways to do this without pneumatics. If we wanted to still use this, you can do versions of it where you have a servo moving this in and out. And that is possible. You can have a full motor moving it in and out if you really want to. It's probably a little heavy to do that. But there are a few different applications where we can get that same braking mechanism. But also, this the brushless motors that we have now, like the Krakens and the Neo Vortex and things, are their brake mode, even when power is off, is just a lot stronger. So in the last few games where we've needed to climb, we've been able to either have some sort of mechanical latch set up, or just use that brake mode of the motor to be able to hold us up. The last little part of the gearbox here is you do have an encoder here. So again, they didn't have them built into the motors. So we're going and getting the position of our whole system off something that'd be like a shaft in here, maybe a piece of surgical tubing or something else to hold these together, to connect the encoder to that shaft. And so they could sense how much the elevator had moved up and down. Okay, so let's look at the elevator itself. Some of the basics of the elevator are relatively easy to make sheet metal components, so they didn't use COTS bearing blocks like we have now. Their actual bearing holding are just this little flat sheet metal bracket, which you could easily make on a CNC router or laser cutter, or water jet. And then same with the lateral one here. So being able to like kind of have that sandwich on both sides of this tube, and then just a bolt holding your bearings on. And the same thing up here. They did go ahead and put this into the tube, so they did have to do some work on the tube to cut this out. But you could easily just not have the tube be as high, and then you can just cut it at a straight line. Like this part over here doesn't actually do much for you here, other than get you a little bit, maybe this extra hole if you couldn't get there if you cut it all the way off flat. The part of the tube manufacturing that they did need to do is as we get into the belt, they have these cutouts down here where they cut into the tube to allow the belt to run through and actually do our lifting. We'll look at the belt in just a second in more detail. But again, they use pretty simple construction. It's just this 2x1 setup with flat plate. So again, these are all doable on the router or water jet, relatively easily, including like the lightning holes to get a little bit better CG. They're able to lighten just a little bit. And then the carriage assembly uses the same concept. So they do have some 2x1 built into this. And then they have these outer plates that are thinner, mounted onto that. So these end up being 1/8 inch aluminum. And so you have an 1/8 inch aluminum plate on the front and the back, and they're able to integrate the bearing assembly here, and then some of the mounting they need too. So they actually mounted the motor controllers for their intake up on top here on the carriage itself. And some of the other, the bearing assemblies like here and here are mounted as part of their whole intake, so you can integrate all of that together. Nice simple crossbars, nothing too hard, just hex shaft that's been tapped, just the rounded hex shaft. And then here, down at the very bottom, they have this piece that rests in here, and I believe there's a sensor in there. Yeah, so there's just a limit switch. So this is how they know their elevator's all the way down, is when it just hits this limit switch, they know it's full down. Okay. Looking at the actual belt path, because that's one of the more interesting parts of this. So this is a continuous elevator. What's the easiest place to see that? Let's remove this beam. There we go. Okay. So from the gearbox here, they have a belt out to this pulley, and then this pulley here does the same thing out to this one. And then you have this belt set up which they did a good job of catting the whole thing for us. There we go. Okay, so there's basically, this is half of the system. There's another identical half running on the other side. These are one continuous belt. So this is the end of the belt, and this is another end of the belt. So this is one incredibly long belt, right? It goes all the way up, over the pulley here, all the way back down, up over the pulley here, all the way back down. Does the U here, and then continues and does it all again on the other side. So a couple things they did really well. So they're getting a full 180 degrees of pulley wrap here. So you have a lot of those belt teeth engaged on the pulley. That allows you to transfer a lot of that force and torque very nicely. This is also how they get their both pull up and down. So this bit that comes here and gets mounted through in the middle here is how they're able to use the motor power to actually pull it down. And the part that goes up this outer side is what they're doing to be able to pull it up. Because it is continuous, they can, basically the system's going to try to move in whatever is the easiest for it, so whatever has like the lowest load. So in general, that means it's going to move the carriage up first because it doesn't have to move the weight of this inner stage if they don't need to. So the carriage is going to come up first, and then the rest of the elevator is going to go up once this can't go up any higher on its own, like once it runs into the top here. And then it'll keep going up with the rest of it. Let's look inside here a little bit. So the biggest part of this path is to do this all well. You don't need any pulleys up here, so these are just running on, they don't actually have grooves in the pulleys for where the belt is. These are just running on smooth backing. And you can do that everywhere because you're not actually trying to transfer power through any of this. But you do really want these to all be parallel to each other so that they don't change distances. So the more that these can all be vertical runs of belt here means that you're not going to have too much. So there ends up being a little bit of angle, and that's normally okay for belt tensioning and things as long as it's not too bad, but you don't want these running at a really severe angle. You want these running as close to straight as you can. Especially the, which ones need to be vertical? So this one here is most likely vertical, I believe. We can check its angle. Yeah, so that's parallel distances straight. And same with the other one on the other side of that pulley, as those are the ones that are going to change their length as they go up and down. If they were at a severe angle, you could potentially change how much belt you need in those different spots, and then at some point, you'll either be too loose at the bottom or too loose at the top, and that would not allow you to have a very functional system. Let's bring that tube back. Yeah, so you can see they did have to do some amount of manufacturing on the tubes themselves. This is relatively easy to do. We could do this on our CNC router and cut through here if we needed to. And then a lot of the actual places where everything's being mounted is done off these larger plates to hold everything in place. So this one's a little bit more because you do have to do the cutout on in the middle. But again, with like a tube jig and a CNC router, all of that's doable to cut and drill the holes for something like that. And then for belt tension, they do that here by folding it over. And I believe, yeah, and so it's folded over, it's clamped to these blocks, and then you have this screw here that you can tighten, and that brings both sides of this belt closer together, and that allows you to tension it and get it just right so that it has grip on all the pulleys and everything. Even if things change a little bit in length or you don't have quite the right number of the amount of belt on it, you can still get it correct as it's sliding. And so then you have the bolts going through here that hold the whole tensioner on. inside those sliding gaps that you have down here. So the whole system kind of slide and tension everything. Let's see. I think these red wheels, I didn't talk about these, but I believe these are custom. I don't think anyone was selling these at the time. So they just needed a much larger wheel than what was sold, because I think about 4 inches was the largest compliant wheel they could get. And so I believe they made a custom wheel here. Yeah, very likely that was either water jetted, so they could have this like custom pattern in that they could put a hub in. So then they have these like hub parts that they're able to bolt through. So this could be done as a water jet. You could also like 3D print something like this now out of like TPU, one of the flexible filaments if you wanted to. I think there are a few more. You can actually buy larger compliant wheels now as well. All right. Is there any other part of this that we cared too much about? So there is a little bit here. That shouldn't do too much. That's just like spacing. I think that's most everything. Oh yeah, with the cable chain. Cable chain and climber. I think that's most everything for this. This is going to be a relatively short video. So the cable chain here is how they were able to organize the wiring. So for the elevator, you pretty much have to go, you want to use all the length that you have. So you're going to run your cables up as tall as you can for like your starting height. And then you run them back down to your carriage itself. And that basically gives you the ability to double your height. So you have it because you run it all the way up, and then you have it run all the way down, and then when it unfolds, you take this whole first part of your height and move it up the other side. If you need to more than double your height, the cable management gets a little bit trickier. You need to either do it in multiple stages or have some other way to have more cable here to be able to take up than just what you can like lay out in a nice up and down energy chain like they do here. So this is modeling those like energy chains where you have individual little segments that can rotate together. And then they have a guard to make sure that like as they're driving around fast or spinning, this cable chain isn't trying to like fly away or loop out at all. So it's inside this cage. They wanted to make sure that this was very light. So this is probably one of the more complex machined parts on this robot. I'm not sure if it started as a U or as a box tube, but either way, they have a whole face missing here, so it may have just been purchased as a U channel. And then they went in and machined some mounting holes. They also machined quite a bit of weight lightening and weight reduction parts, including even just doing some skeleton, where they go out and pocket this and leave that thin little bit of material here on the inside. But they almost certainly machined this all the way through. So they machined off this face, and then with a long enough cutter, they went through and machined this next part on a rather large mill, or in multiple operations. You could set it up and then like do half of it, then move it and do the other half. That is possible. This is definitely one of the more machining intensive parts for most teams. If they wanted to replicate this would be a little tricky. I definitely wouldn't want to do this on a router, trying to go through this and cutting out this inside part. But I'm sure you could on some CNC routers. In addition, they were able to just make a very simple climber mechanism that allowed them to climb on either side of their robot. It was just an extra piece of 1/4 inch aluminum bolted through on standoffs, and it was able to hook on to the climbing pole and then just lift them up from that first stage that does the moving, right? So they're not mounting this to the carriage at all. It's only on that first stage, so that normally has better bearing overlap, and you're less worried about like the entire carriage itself falling out of the elevator. So if like, if you put too much stress on some of these bearings and things, where you don't have that much distance between these two bearings, you could bend things or flex things to where the whole carriage may want to fall out. Climbing on the first stage here means you have a lot of distance between your bearing here and the one way down low, way down here. So once it's fully climbed, you have a lot more support And so for that little bit at the beginning when they are close together, you could have some issues, but probably not. They have enough bearing overlap onto the face width here. So they have the double stack bearings, so they get 3/8 of an inch or so of contact there. So it's not like if you're just using the single bearing, you could imagine it'd be pretty easy to like slide past it if something flexed. The extra bearing gives you that little bit more room and contact area on the tube. But yeah, for not having too much more than just 2D cut plates and extrusion, a few, lightened again, able to do some bolting, but they use 1x1 in good places, so they basically just use this as a spacer. They have a little cross beam here to try to take twist out of the elevator, hold the two sides together without adding too much more structure. So having it here down at an angle is going to do that a little bit better than just having it go straight across. Kind of already have the cross beam up top here. So yeah, so it uses a lot of relatively simple parts, all things that can be 2D cut on a laser cutter, CNC router, or water jet, and then pretty much just into tubes. So there's not a lot going on, but they were able to build a very high quality robot, and being able to use the swerve drive that they had and as an advantage over a lot of teams who are still doing tanks. So they could be a little bit simpler. They didn't need as complicated of an intake, because they could just like drive sideways a little bit and still get the cube. Yeah, they built it to where the elevator was far enough back and wasn't like front heavy, so as it was rising up, they weren't like trying to tip over forward. There's some match video of them. You can see it's a little bit